And then I was asked, what kind of topic would you like to talk about? And I said, if it's a public lecture, I think it would be very appropriate to talk about the Nobel Prize in Physics for 2019, not only because there is fascinating science behind it, behind the two topics, but also because they speak to us as humans, both topics, they speak to us. And that's what I will try to do. Forgive me if I skip some things or if I go very quickly on some things, because these are two huge topics. Each one of them is, but I have been asked to limit it to about 45 minutes. I'm sure I'll go beyond, hopefully not too much. But it's very hard to address these topics in a scientifically sound manner and at the same time sort of quasi-complete manner in 20 to 25 minutes each. You will see, extremely difficult. The Nobel Prize in Physics for 2019 was given to these three scientists. James Peebles on the left, and I will explain shortly what James Peebles' contributions were. Suffice it to say for now that his contribution was in the physical grounding, the physical detailing of Big Bang, early universe theory. And we'll get to that a little bit later. Michel Mayor and Didier Queloz are two Swiss astronomers who became famous and now historically have gone into the history books because they were the first people to discover a planet outside our solar system orbiting around a sun-like star. So these two were, let me begin with the exoplanets, simply because in the title of the talk it was exoplanets first and then the early universe. So we go with the exoplanets. The first discovery was done in 1995 by these two gentlemen. These are Swiss scientists, as I mentioned, and they were given the prize literally, as the Nobel Prize Committee said, for discovering the first exoplanet orbiting a sun-like star. And that in itself, you will see, is a great achievement. And opening up a new, very important field in astronomy. This was a breakthrough, as I will try to explain to you. They spent their scientific careers at the first one at the Observatory of Geneva, the other at the University of Geneva. Didier Queloz, who is here underneath at the bottom image, was actually a PhD student of Michel Mayor, and he is the one responsible for developing the technique and making it work to extract the information that shows us that we do have, yes, a planet around that particular star over there. You may think, what's the big deal about that? Let's just look over there. If there's a planet orbiting a star, we should be able to see it or something. But it is much, much harder than that. This is where that planet is. You can try to look for it with your eye if you like, or at least know where roughly it is in the sky. This is the famous square of Pegasus. This is Andromeda, and you would have the Andromeda galaxy, which is the only galaxy that we can actually see with our naked eye from the northern hemisphere from very good locations. Not Lahore, sorry, and certainly not in Sharjah, I have to say. Sharjah is probably even worse in terms of observable conditions. In any case, this is Cygnus, as you can see. This is the famous summer triangle, the three very bright stars that we see very often in the sky. You can see them also these days. Vega, Deneb, Altair, all three having Arab names, just to say in passing. In any case, 51 Pegasi is the star that would be about here, and the star will be around it. No telescope, not even, forget our naked eyes, forget binoculars, no telescope, sorry, Romayan, no telescope would ever be able, not would ever, I shouldn't say would ever. Right now, no telescope can see that planet. And I'll explain how it was detected and why it cannot be seen with a telescope. This planet was a large planet. The first planets that were detected or discovered were large planets. These are called hot Jupiters because they are significantly large, more or less the size of Jupiter, some of them much larger than Jupiter, some of them a little bit smaller than Jupiter, and orbiting very close to their stars. And so that makes them very hot. So they look like this. None of these are images, by the way. All of these are, of course, paintings. I hope everybody realizes. All of these are just nice paintings describing what they would look like. They are sort of good representations. It's like we take an artist and we say, okay, here are the here's the information about this system, the star and its planet. Please paint it for me, as it would be if you respect this information. What is this information? This is the distance to that star that I mentioned, 51 Pegasi. B, we have a tradition in astronomy to call the planets when they are outside the solar system by the star, and then the letter B, C, D, like that. Okay, so B means the first planet that we have found orbiting this star. If you find another one, then we'll call it 51 Pegasi C, and so on. This star this is why it's called sunlight or solar type planet, has a mass of about 1.1 the mass of the sun. The mass of the planet is about half the mass of Jupiter, so that's about 150 times the mass of Earth. So this is a relatively big planet. And it orbits, the distance between the planet and the star is only about 8 million kilometers. Let me remind you that Mercury orbits around the sun at roughly, to simplify, 50 million kilometers. So this one is almost is about 6 times closer to its star than even Mercury. The Earth orbits around the sun at 150 million kilometers. This one is only 8 million kilometers. And that's what makes it hot. So it's a hot Jupiter orbiting around the sun-like star. Okay? So that's the first planet that was discovered. And from that moment, sort of the floodgates opened. And you will see how. But before that, since this is at least, it's a public lecture, but at the same time, it's given at the university, so I have to give a little bit of science behind it and explain. By the way, I am delighted to see kids in the audience. I am always very happy to see kids. So there's like 3 or 4 kids, that's wonderful. When we tell people that discovering planets outside the solar system is extremely difficult, they do not always understand why. They think, don't you guys have big telescopes? Why don't you just point your big telescope? Don't you point your telescopes, and then if there is a planet, you see it? And I say, okay, there are actually a number of planets. There's like now, I think, maybe 2,000 planets out of a total of about 4,000. In the last 25 years, since that first historic discovery, we have raised the number of confirmed exoplanets to about 4,000. So you can see the explosion. Out of the 4,000, I think there's maybe 3,000 that have been discovered through what we call direct imaging. Let me explain what this direct imaging is. If I show you an image like this, see, there's no image. See, it's very hard. Froze. Oh, there's something called suspicious file detected. Oh. I didn't like my file. There are no aliens as yet, so I don't know why it doesn't like the file. Okay? All right, good, thank you. So if I show you this, here's what this represents. This represents a star that we are trying to look at, and by the way, this point has just been added just to show you what we are talking about. But it has been blocked completely, so we're looking at the star and we block out the star. You say, why? Because I want to see what's around it. If I look in that direction and I see the star, then there is no way I can see the planet around it, because the planet is going to be infinitesimally bright compared to it. Very, very faint. Yes? So we block out. It's just like if you're trying to see a bird passing and there's the sun over there or something, you block out the sun so you can see the bird passing. That's what we do. So we do a blocking of the star, and we block out this whole area, and then we see a whole bunch of points like this. And what's this? This is all noise. This is noise from the instrumentation. How do we know it's noise? It's because if I repeat the observation a minute later, all these points change. Noise. Noise, by definition, is random. Okay? Except, if I ask, and this is impossible to do with eyes or even with bright students, okay? you would have to ask the computer and say, okay, here are the images. Take image after image after image after image, and tell the computer, search for all the points that are changing, remove them. And if you find a point that is actually always there, always there, always there, always there, then you see some points that are, this animation is a collection of data taken over 7 years. Okay, so you collect 7 years of images, tell the computer, okay, ignore all the random fluctuations and changing, and tell me any point that is actually always there, and better yet, if it moves in the image, like in here, for example, if you focus on this little square, you would see that there is a point that is actually moving like this year after year, likewise here. So this is what we call direct imaging, and you can see why it is extremely difficult, But this is why we invented other indirect methods of detecting. There's like a half a dozen methods, but I will focus on the two major ones, in addition to the direct imaging one, which everybody likes to understand. I show it first always to show the difficulty and why we can't always just take a picture of a planet. And even when you are able to see a picture of a planet, it's barely a pixel, okay? 1 pixel. So that's the planet. The second method is called radial velocity. It's based on Doppler. So for those of you who have done some physics and so forth, this is when you have a source of light or a source of sound or a source of any wave, and if it moves toward you or away from you, then the wavelength that you see or you receive is going to be shifted. Please look with me here. Obviously, this is an exaggerated diagram because, as I just showed you, the stars, even the biggest stars in the biggest telescopes are barely a dot, maybe a little fudge of a dot. Okay? Never anything like this. But this is just to represent, and if you can notice, this planet, as it goes back and forth, or actually the star like this, makes the star wobble a little bit. So it's just like, if you have two objects orbiting each other, then they go like this. But if you have one that is very small and one very big, the very small one is doing this, the very big one is just doing this. But as it does this, it is actually as if I'm the star and I'm doing this. Okay? But as I'm doing this, at some points I'm doing this towards you, and at some points I'm doing this away from you. As I do this towards you, any light that I send you will be shifted toward the blue. And once I do this, any light coming from me will be shifted toward the red. And that's what you see here. See these lines? These lines, which represent the absorption of light through the atmosphere of the star, is shifting toward the blue, shifting toward the red. This is when the star is moving toward you, away from you, as it goes around itself, around the center of mass like this. This, believe it or not, is the way we have discovered something like 30% of the 4,000 planets I mentioned earlier. We don't even look at the star. I mean, we look at the star, but we receive the light from the star, and we just analyze its spectrum. We don't care what the star is doing, we just receive the light, and make it go through a spectrometer or a spectroscope and just analyze this back and forth. From the back and forth and how much it is going back and forth, we infer what other object is out there making the star do that. Okay? So we never see the planet itself. We look at the star, and from whatever the star is doing, we infer the planet. So that's one. And that's, by the way, that's the technique that Didier Queloz, I mentioned earlier, developed and got to work accurately enough to really get a result about a planet orbiting a star, the planet we have never seen to this day. Okay? But we know for sure it's there. The other method is the so-called transit method. Transit method, again, this is hugely exaggerated. So imagine there's a star like this red dot I have put in here, suppose, like this, and there is a planet that goes around it. Every time it moves in front of it, compared to you, so if you're looking at this star, all you see is the star, and then all of a sudden, when something goes in front of it, the light that comes from the star drops a little bit. Drops, because it got sort of partially eclipsed, if you like. A little bit of it got blocked by the planet. How much gets blocked? If you have a big star, big planet, like Jupiter, passing in front of it, the light from that star drops by about 1%. If you have a planet that is like the Earth, and it goes in front of it, the light that you receive drops by 1% of 1%. Okay? And yet, we have about 70% of these 4,000 planets that we have discovered in the last 25 years were discovered through this method. So that's how we are discovering these planets. This is sort of the latest. This is, you can see here, this is cumulative detections per year up to about 15th of December. This is the latest histogram, data, statistics of all the planets. The green stuff here is all the ones that were discovered through the method I just described. And the red one here are all the planets that were discovered through the other method that I mentioned. And as you can see, there's a whole bunch of others, including microlensing. The imaging is the first one that I mentioned, which I said is very difficult and extremely rare, and that's what we do. Now, I want to show you this animation. It'll go fast, so please look. These are the planets that we knew by year. 1995, now first planet, or first exoplanet, over here. These are the big planets. See, this is mass here. Big planets. At first, our techniques were not so refined, so we could only detect the big ones, because the big ones have a bigger effect. And then we refined our techniques, and we started to be able to discover smaller and smaller planets. So you can see this will fill up, it will repeat. It will first fill up over here, big planets we are discovering, closer to their stars, farther from their stars, okay? And then we start discovering smaller planets. This is the one we are most interested in. This is the size of the Earth. The Earth is here, so this is size of the Earth, distance like the Earth. The ones we really would love to discover are the ones that would be about here. Or this is Mars, this is Venus, this is Mercury, something like this. Why? Because these are the ones that would be rocky, solid, would have a reasonable atmosphere, possibly liquid water, if they happen to be in the habitable zone, in the right zone, around their stars, etc. And that's what we are aiming for now. So this is up to, you will see this will stop at about 2017. By 2017, I think we had about 3,000 planets. Okay, so this will stop and it will say, see, numbers are increasing very fast. Then here it starts sort of exploding because we launched a satellite, almost 3,000 planets. Okay, so let's move now. The next animation, because it will go very fast, so let me explain to you what the next animation, which is exactly like this, will do, is to show you what will happen in the next 15 years. Okay, so let's look at this now. So this is what we have now, 2007, or at least what was there 2017. Now we start to get in the tens of thousands of exoplanets. By the time we get to 2035, there's 120,000 exoplanets. Okay? Now you say, okay, we're 120,000, that's not impressive, but good for you guys. But the point is, as I said, what do we want? We want planets that are not too big, and not too close, not too far. Okay? So, will we have planets that are at about here? Yes, you see, this is populating. Oh, this looks great. You see? And we will even have, these are Mars-like planets. Okay, over here. So you will have plenty of planets in the next 10, 15 years. Those of you who are students and are interested in astrophysics, this is your time. Really. Because these planets now, we won't just, okay, let's discover more planets. Here's an Earth-sized planet. Okay, hey, great. Here's another Mars or something. No, we will want to characterize these planets. And I don't have time today, but I wish I could explain to you how these objects, which we don't even see, 99.9% of them we don't even see, right? We discover them indirectly, as I explained. We will be able to characterize their atmospheres. We will be able to say whether they have atmospheres and what their atmospheres contain, what kind of gases. Do they have oxygen, ozone, water vapor, methane, all kinds of gases that will be biosignatures. Okay, that's what we are aiming for. So watch the news. Okay, maybe not tonight, but over the next few years. All right. Second half of the Nobel Prize was given to this great scientist, James Peebles. James Peebles, who spent his entire, he's from Canada, then went to the US, did his master's, PhD, postdoc, spent his entire life at Princeton. Anyone who has been to Princeton would understand why. Okay. Wonderful place, really wonderful place. Of course, the place where Einstein spent his last, 25 years or something, and had long walks with Goodell, and yeah, I don't want to get emotional. But James Peebles, Canadian-American scientist, received half of the 2019 Nobel Prize for theoretical discoveries in physical cosmology. I'll try to unpack this in a minute. Over the last 50 years, he spent 50 years working on this. Now 84 years old, still active. He spent all of his academic life at Princeton, from master's and doctorate to the present day. So, what did he do exactly? Cosmology in early 20th century, I always love mentioning these quotes. Ernest Rutherford said, in early 20th century, he said, "Let me not catch anyone talking about the universe in my laboratory." Because at that time, talking about the universe in cosmology was essentially talking about nonsense. It was just speculation upon speculation, okay? And he wanted people to focus on research. It's like your PhD or master's supervisor walks into the lab one day and finds you talking about football. Say, what are you talking about? You're spending your time and drawing diagrams on the board on tactics and stuff. I want you to do real science. And then another quote, which is very interesting. Edward Wright, a current UCLA cosmologist, said only one cosmological fact was known in 1917. You'll see why 1917. Namely, that the sky is dark at night, and Einstein ignored it. So that's how much data we have about cosmology. Remember this, because you will see what kind of data we now have in 100 years. 1916, cosmology became a theoretical science. How? Because Einstein wrote his equation. And then he decided that this equation can apply to the inner solar system, and he applied it to the inner solar system and figured out the orbit of Mercury, and showed that the orbit of Mercury deviates slightly, but enough from the orbit that you get using Newton's equations, and therefore you can test this. If you find that the orbital parameters of Mercury are slightly different from what Newton said and actually fit what Einstein says, it means Einstein is correct. Then he says, oh, but we can apply it to even bigger systems. At that time, people hadn't even discovered galaxies. Okay? So he said, okay, let me apply it to the whole universe. So he applies it to the whole universe, and he finds that the solutions, remember this is in 4 dimensions, so this is 3D plus time. And in time, these solutions show you that this universe, this entire system, which includes mass and energy and has curvature. Remember, general relativity says if you have mass and energy, then that mass and energy curves the space around you, and that space has to be described in a 4th dimension time. And when he solves it, he finds that this is actually dynamic. It evolves in time. And he says, that can't be. How can the universe be sort of growing? Shouldn't be like that. So what he does is he modifies his equation. He adds this term here, called the cosmological constant, in order for this equation now modified to give him a static solution. So now the universe is not growing. Remember, this is before expansion of the universe, before Hubble and all of that. But at least we now have equations. Now we can do serious mathematics, at least. Not yet physics, but at least mathematics. Under certain assumptions, how much energy is there, how much mass, and so forth, which nobody knew. How much mass is there in the total universe? How much energy is there in the total universe? So this, which represents the mass-energy tensor, was like an unknown. It's like, okay, let's put a value there and solve and see what happens. And that's what this fellow here, Alexander Friedman, Russian mathematicians, decided to do. Let's take this equation of Einstein and solve it under different conditions or assumptions, and we find that the universe could actually grow indefinitely like this, or stabilize and become constant, or actually stop evolving and growing and then collapse upon itself. So there's different possibilities for this universe. Which one is our universe? Nobody knew, because we didn't know how much mass and how much energy there is in the universe. Then comes this fellow, Edwin Hubble, with his big telescope in California. Oops. And Hubble first, in 1923, discovers other galaxies, realizes that there are other objects out there. Remember Andromeda I mentioned to you earlier? He measures the distance to the big achievement in astronomy, measuring a distance, believe me. You tell people, you say, 1923, Edwin Hubble was able to measure the distance to a galaxy. You say, why is that a big deal? Huge deal in astronomy, measuring distances in general, especially cosmic distances, large distances. You will see later what kind of problem that is. It's a nightmare to this day, okay? Anyway, so when he measures the distance to Andromeda, he realizes that Andromeda is outside of our island universe, Milky Way. So that's a different galaxy. And then he starts measuring other objects which we can see with our naked eyes, but he can see with his big telescope, and he finds the techniques. There's a whole history around this, fascinating anecdotes, and he finds that there's lots and lots of galaxies out there. So the universe becomes millions of light years in size and billions of years in age. Now cosmology becomes an observational science. But it gets even much better, much better, because as he measures these galaxies and their distances, now he can do spectroscopy. Remember, the light that comes from each of these galaxies, take a look at its spectrum, and what he realizes is that most of them, especially those that are far away, have their spectrum shifted toward the red. This is the famous. By how much they are shifted toward the red turns out to be proportional or related. This is his early data. You can see how crummy it is. Early data, figuring out the velocity of each galaxy and the distances of each galaxy, and you can see that there is a linear relationship. As time passes, as we refine our techniques, the plots become much more aligned with the line. And now we really have an accurate, strong correlation relationship between velocity of these galaxies and distance of these galaxies. This is known as the Hubble Law, Hubble's Law of galaxies. Now, quickly, people realize that the only way you can have galaxies that are actually moving away from us and from each other with velocities that are proportional to the distances is by having the entire field extended. That's the only way. And so that's the discovery of the expansion of the universe. That is 1929, roughly. 1907, this fellow, Georges Lemaitre, a Belgian scientist, physicist, proposes that the universe, since Friedman had already showed and Einstein had found but didn't like it, any solutions that say the universe starts and grows, starts and evolves. Then does it continue to grow? Does it stop and collapse? But it starts at a point. So Lemaitre says, I think the universe must have started from a little region, little size. Not a point, because if it's a point, then everything is infinite, and physicists hate infinity. Okay? Infinity is a crime. You can't have infinity. Anytime you solve an equation, you get infinity, check again. You've made a mistake somewhere, either in the solution or in your assumptions. You can't have infinities in the universe. Okay? So he says, maybe not an infinite, but maybe some little size. So he calls it primordial atom. It doesn't mean atom as in atom, what we understand today. It means a very little size, and the universe was very tiny, all condensed in that little size, and then increased. By the way, when he gave a seminar one day, and Einstein was in the audience, and he presented his ideas, and in the end, Einstein went to him and he said, your mathematics is wonderful, but your physics is awful. Because Einstein didn't like that kind of expansion and so forth. Later, he realized that he was very wrong, and he called it his biggest blunder. But anyway, 1948, oops, too fast. This fellow, George Gamow, Russian, immigrated to the US, and his PhD student, Ralph Alpher, proposed and developed what we now call the Big Bang model. At that time, they didn't call it the Big Bang model. They just said a physical model of a universe that starts very small, with high density and high temperature, expands, and as it expands, it cools, and as it cools, all kinds of physics happens, and we can try to figure out what happened in all that time. That's the Big Bang theory, essentially. Okay, not the TV series, okay? The real theory, Big Bang theory. We start with a very small size, high density, high temperature, let it expand, do all the nuclear reactions and the thermodynamics. It sounds easier than it is, as I say it like this. Do the nuclear physics. Yeah, you do it. Do the thermodynamics. Yeah, sure, easy. Plus, remember, all of this is in 4D and curved, okay? But that's what you need to do. But Gamow, being the joker that he was, he had a refined sense of humor, he said, your name is alpha, my name is gamma, we need a beta. And of course, there was a great scientist who later received the Nobel Prize called Hans Bethe. So Gamow adds beta to the paper, beta not having any idea of this paper. So now this paper is in history known as the alpha beta gamma paper. So that just shows you that science is fun. Even theorists are fun, okay? Not just the experimental. So that's the Big Bang. Now, so this is sort of the whole history of the universe in galaxies, and today we are here. And today there's another thing, which is the acceleration of the universe, which we can talk about later. Now, how do we know that this is true? That this whole story of this universe growing like that and expanding and this nuclear reactions that I mentioned and thermodynamics, and how do we know this is true? Because there is observational evidence for the Big Bang. Indirect observational evidence. So this theory, Big Bang theory, of course, with all its physics that it does and the mathematics, gets some results and says, okay, after a certain time, here's how much hydrogen, helium, lithium, beryllium you will get. Here's what kind of temperature you will have in the universe. Here's what kind of radiation would have occurred. So, guys, go and observe and measure. If you find that what you measure and detect is in concordance with what we theorists have told you, then my model is correct. If you find that, oh, you're very wrong, then I need to go back to the drawing board, right? That's how science goes. And indeed, when there was almost a serendipitous discovery of this radiation that permeates the universe, if you observe in different directions, these guys had made it's a long story, very funny story, of how they measured, how they realized that there is some background, they called it. At first, they thought it was some kind of a noise or some external source that is producing that kind of radiation. But they found that there is some radiation in the microwave band through their radio telescope. And they kept checking and checking and checking. And then somebody told them, and they happened to be near Princeton. Somebody told them, there's a bunch of guys in Princeton who have been doing some calculations and talking about some kind of a background radiation. So they went to them and said, okay, here's what we have observed. And the guys looked at them and said, oh my God, this is confirmation to what we have been talking about for 20 years or 15 years. And so that radiation, which is everywhere, if you ignore all the radiation that comes from stars, galaxies, everything, there is some remaining radiation that is everywhere in the universe, in all directions, identical. For now, it's identical. In a moment, I will say slightly not identical. But for now, identical. And not only is it identical, but its characteristics that you can measure and do spectroscopy and all of it is exactly what the Big Bang theory predicts. So that's a huge triumph. Another prediction, which turns out to be extremely well confirmed, I think this one is even more impressive, at least at this point. In a minute, I would say that this radiation becomes even more impressive. So there's two big lines of evidence, and each one becomes more impressive than the other. So this second one is most abundant elements in the universe. If you ask people who have had some astronomy or astrophysics, and you say, what is the most abundant element in the universe? They say, hydrogen, of course. They say, don't you know, 90% of the universe is hydrogen. I say, okay, good, very good. Okay. Now, if I have students, then I ask them, what's the second most abundant element? And they say, helium. If they don't say helium, woe to them. Helium. How much helium? 9%. Okay, good. You're good, you're good. So far, so good. What's the third most abundant element in the universe? That's when it becomes a bit tricky. And most people will say, maybe this is the third one, lithium? No. There's a whole line of reasons which I can't explain now why lithium is not, even though it's the third in the periodic table, is not the third most abundant. Then which one? Maybe beryllium? Certainly not beryllium. Beryllium is very fragile. Okay, which one? Maybe carbon. Oh, carbon. There's plenty of carbon. Life is based on carbon. Sorry, no, not carbon. It's oxygen. Oh, there's a whole long story. It's a whole course. I'm exaggerating, but almost. Because carbon and oxygen are actually made in the stars. And there's a whole series of reactions and stuff where you figure out how we get the carbon, how we get the oxygen, and everything else. Okay? But the elements that were made in the Big Bang were hydrogen, which was made from the building blocks, from the protons, which themselves were made from the quarks, and helium, because the protons started to react together while the universe was still very hot and very dense, started to react, produced lots of helium. And thank God the universe continued to expand so that the hydrogen didn't all turn into helium, because we wouldn't be here, right? Suppose everything had turned into helium. Helium doesn't do any chemical reactions. You would never get anything out of helium. You would never get any DNA, cells, whatever, all solid stuff. You can't. So, at some point, the universe stopped expanding, so you were left with a lot of hydrogen, some helium, and tiny amounts of lithium and other stuff. Guess what? The Big Bang Theory can calculate exactly for you how much hydrogen, helium, I'll get to this in a minute, hydrogen, helium, oh, I didn't put this, this should be a superscript, so this is hydrogen 2, this is deuterium, and this should also be a superscript, so this is helium 3, and this is lithium 7, okay? This is how much you get, 10 to the minus 9, maybe I prepared my slide a bit too fast. It's 10 to the minus 9 in lithium, is 0.004% of hydrogen 2, and guess what? The Big Bang Theory calculates it for you this precisely, and when you go and observe everything in the universe and figure out how much hydrogen 2, this is the isotope of hydrogen, deuterium, exactly that. This is the graph that I love so much. These are the calculations. This is helium, this is deuterium, this is hydrogen 2, also called D, this is helium 3, and this is lithium 7. And these lines over here, there's a line you can barely see, that line over there. And there's a line here, and there's a line here with the uncertainty. The thickness is the uncertainty in the measurement. This is the measurement. And this here is lithium 7 over here. And there are two different assumptions, but doesn't matter. Now, what I want you to notice is the measurement and the calculation and the measurement intersect here. For this guy and this guy, they intersect here. For this guy, calculation, and this measurement, they intersect here. And for this guy over here, and the calculation, they intersect about here. And they all fit nicely with this exact parameter of the universe. This is an extraordinary type of work. When you have four things which are extremely difficult, both to calculate and to measure, and you get them to all agree like this with your parameters, it is an extraordinary achievement. Then you have these guys who actually got the Nobel Prize in 2006 by refining the map of radiation that I was talking about earlier. Remember I said everyone starts to become more impressive than the other? So now we go back to the map, to the radiation. Now we're able to do a mapping of the radiation, mapping of the entire sky, the entire universe, in every direction, okay? So as you can see, when you see some colors, it means there's some slight differences in the characteristics, in temperature. How much of a slight difference? 1 in 100,000. Okay, that much difference. Guess what? That much difference is extremely important. If we didn't have any difference between them, there would be trouble in the lab. If we had more difference than that, the theory is in trouble. So, and then they start refining it exactly. These guys got the Nobel Prize. Now you say, what does that have to do with it? And we continue, same story. Look, 1992, 2003, 2013. By the way, the guys who got the Nobel Prize in 2006 was for this. And now we have much better. Much better. Yes, you will see why this is also important. Now back to James Peebles, who received the Nobel Prize this year. When on the same day when the Nobel Prize was announced and Princeton organized a press conference, one reporter asked James Peebles, said, what part of your work do you think the Nobel Prize Committee decided this is worthy of a prize? It's not one, it's my entire life that I cannot tell you, this little specific calculation is really what made me, a history writing person. This is not what got me into history. He said, my entire life. What was his entire life's work? One, what I'm calling the dissection of the cosmic microwave background, that map. So now, over the last 20, 30 years, James Peebles does the theory behind these fine details of the microwave background radiation. Why? Because, before I get too further, because that is how you can really figure out how the galaxies and the stars formed in the early universe. By now, what we mean early universe is the first 100 million years. But those 100 million years that led to formations of galaxies and stars here and there were because there were some slight differences in the concentration, in the densities of matter, which were inscribed, which now you can see in the map of the radiation. So the map of the radiation is telling you how much of a density fluctuation there were, and the density fluctuations, people do the calculations and tell you how and how much stars and galaxies you can get. Without those fluctuations, you cannot explain galaxies because everything would just be completely homogeneous. Why would there be a galaxy or a star here when everything is equal everywhere? Everybody understands? So that's the first thing that James Peebles spent his time trying to figure out the details of this microwave background radiation. It's not just, oh, there's radiation everywhere, okay, guys, go home. No, there's all kinds of details to this microwave radiation. Number two, participating in the calculation that I mentioned a moment ago. He didn't just do it by himself, but he had lots of papers trying to calculate what, under various assumptions, in particular pointing out the importance of dark matter in the evolution of the universe and taking that into account. There is something in the universe called dark matter. I can go back to that a little bit later. But James Peebles was the first one to realize that if you don't take dark matter into account in your evolution of the universe and figuring out what will happen to the radiation map, the distribution of the radiation in various directions, and what you will get in terms of different nuclear elements, you will get wrong results. So you have to assume that there is some dark matter and how much. Here's another thing. So this is what I'm calling the dissection of the radiation map. So the radiation map can look like this. And so you start to sort of zoom into it, or it can look like this, or it can look like this. Meaning, you can go into big, medium, or small sizes. And you start to see how much difference is there at the very smallest sizes, how much difference is there at the medium sizes, and how much difference. This is called multiple expansion. So when you take the radiation and you do some kind of a Fourier transform, those of you who do the science, you do a Fourier transform, then you get different components of this radiation, and each component is telling you what is happening at different scales of the universe. And the analysis of these different scales of the universe is going to tell you what kind of content there is in the universe in terms of normal matter, dark matter, and dark energy. This is one of the main things that James Peebles worked on in the last 20 years. Now, matter in the universe. So most recent results, so what have we in this universe? Well, it turns out if you do all this analysis, uranium makes up about 4.9% of the entire matter energy content of the universe. And you say, well, and the rest is what? The rest is dark matter to about 26.8% from the analysis I just showed you, and 68.3% dark energy, which is responsible for the acceleration of the universe, which we discovered about 20 years ago. So the universe is not just expanding, actually. It turns out that it has been accelerating in its expansion over the last about 5 billion years or so. So it expanded and then slowed down for about 8 billion years, and then it started to expand, to accelerate again. And that we only discovered recently. And acceleration means some energy input. How do you accelerate something? You have to pump in some energy, and this energy we don't know what it is, so we call it dark energy. But we know there's a lot of it because that's the only way you can explain how the universe is distributed at large scales. The age of the universe, again, most recent determinations, is about 13.8 billion years, with the uncertainty that you see here. And the size of the universe, size of the observable universe, I should say, has a diameter of twice this much. So this is sort of radius of curvature. So the whole diameter of the universe, if you like, right, is the diameter of the universe that we can see, from which we receive any light, is about 92 billion light years. So these are the most recent results. There's another problem nowadays. This is the so-called Hubble constant. Do you remember 10 minutes? Oh, wonderful. I'm almost done. I thought you were going to say finished. No. The Hubble constant is the rate at which the universe is expanding. Remember the Hubble law? Galaxies, speed versus distance, which I said can only be explained, this Hubble law, by assuming that the entire universe is expanding. That's the only way you can have galaxies at different distances, moving away from each other at the proportional speeds. Okay? That rate, if you calculate the slope, very simple. Slope of that line is called the Hubble constant. Okay? The Hubble constant, this is very funny. I'm not funny. This is really science in its full glory. Really in its full glory. So this is the earliest measurements of the Hubble constant. Very bad. Very bad, very wrong. Very wrong. Way far. Now we will soon be over here. Look where we were before. Like a factor of 10. I'm sorry, that's the technology that we have. And it's very hard. Remember I said earlier, very hard to measure distances? Well, guess what? This is all problem of distances. We can measure speeds of galaxies far, far away 10 times easier than we can measure their distances. Very simple. And that's what produced this. But we started to improve, and so we started to converge toward this value. Yes, but we're not quite done yet. So now, between 1975 and 1990, these are the different measurements, and they are in between, you can see something like 50 and 100. We're sort of converging toward the value about 70 or so, but still lots of uncertainty. We're not quite there. Nobody knows exactly what the value is. This is important because the Hubble constant is essentially telling you how fast the universe is expanding. And that tells you how old the universe is, what is happening now, and so on and so forth. All kinds of things. This is the most basic and most important parameter in cosmology. Very simple. Very simple to understand, very simple to conceptualize, extremely hard to measure. Okay? Now, let's continue. Since 1996, you see now we've improved. We're improving and converging. So we were all over here, and now it's improving, and now we're about almost there. We're not quite agreeing because there are essentially two big methods for determining the Hubble constant, this famous H0. Oops. Here's a plot of the two main methods that determine the Hubble constant over the last 20 years or so, 15 years. So this goes all the way to 2016 here. You can see there are two methods. Big uncertainties, more or less, saying the same thing. They overlap perfectly fine, and then now here we start to have a problem. Because now we have this method. This method is simply the one that tries to determine distances. This is known as the distance ladder method. Try to determine the distance as accurately as you can by going sort of one step to another. Remember, the velocity is easy to determine, so it's all about the distance. And this is the so-called lambda CDM. Lambda is dark energy, and CDM cold dark matter. Okay, so this is the sort of the standard model of cosmology today, with dark energy and dark matter. Put all of that in there, solve, and give me a number. Okay? So when you do that, extract from the data of the radiation map that I showed you, you get this value. And this value with its uncertainty is quite far from this with its uncertainty. There's more than 99% chance that they are in conflict. Not 100%, but more than 99% chance that they are in conflict, these two methods. Two very different methods, two different approaches, two different teams, sometimes more than one team on each, and everybody saying they're wrong, we're right. Of course. Now, last year, or at about 2018, there was a new method that came up. This is related to the gravitational waves measured by this source, from this source. This is a very, very famous source and object, because this is the first time, and so far the only time, that we have measured both gravitational waves and electromagnetic waves from a given source. This is a historic object, okay, known as 170817. Very easy to remember. So, if you like gravitational waves, as these people do, they refer to it as GW 170817. If you're like me, a gamma ray person, then we refer to it as GRB 170817. Gamma ray burst. Which one is it? It's both gravitational waves and electromagnetic waves. But depending on which one you prefer, you refer to it. Anyway, one guy came up with this method, which I have yet to understand, to be honest with you, to figure out the Hubble constant from if you have neutron-star mergers, and you analyze the data that comes from that merger, you can, according to his method, figure out at what rate is the universe expanding. Now, he says, with the data that we have now, because we have only one object, the uncertainty is very large. So he got this value, which is just about 70 here, plus or minus, you see this huge uncertainty. But he says, between now and the early 2020s, within 3-4 years, we will have discovered a lot more of these objects, and we'll be able to reduce the uncertainty over here to this much. And he predicts that the Hubble constant will be just about here. And so maybe both of these are wrong, and the result is actually here. Or maybe this guy is wrong, and the actual result is here, and these guys are very wrong, something. Okay? So this is cosmology today. Summary and conclusions. One, it is incredible what exoplanets, just to go back to the exoplanets part of my talk, it's incredible what exoplanets we have discovered in 25 years. And yet, the next 25 years promise A lot. We get them by the dozen. I'm serious. When they announced, there used to be Kepler, and then Kepler 2, now there's TESS, there's this satellite called TESS, TESS. TESS has just discovered 6 exoplanets. Only 6? It's really going to be by the dozen. But more importantly, it will be the characterization of these exoplanets. What kind of planets are they? Are they rocky, solid, small, Earth-size, Mars-size, Venus-like? Do they have thick atmospheres, thin atmospheres? Are they in the habitable zone? At what distance? Are they orbiting their stars? It'll be an incredible journey. Incredible. For those of you who are maybe just entering astrophysics, I envy you. I wish I was born in 1980 or something. Part 2, it is incredible also how cosmology has progressed in 100 years. From Einstein didn't even remember that the sky is dark at night, to now we can analyze the radiation from the universe to extremely small scales and figure out dark matter and dark energy and an accelerated universe, accelerated expansion, and so on and so forth, reaching amazing levels of details. And yet, more big questions are awaiting answers. What's this dark matter? Nobody knows. What's this dark energy? Nobody knows. We cannot even agree on the Hubble Constant. Incredible progress, but this is the story of science. Always incredible progress, but with every incredible progress, more questions are open. Thank you very much.
Welcome to ask small or big questions.
Yes.
So thank you for a very so the first part of talk we talked about exoplanets, and you showed us a way how the first exoplanet was discovered through shift in the spectrum. So this is because a planet is orbiting its star, so there's a kind of shift in the spectra coming from that star.
Yeah.
So if there are more than one planet orbiting the same star, how do you distinguish it from one planet, or 2 or 3 or 10?
Science is incredible, isn't it? So we have now many multiple planet systems. Many. I don't know how many. Hundreds. The largest number, as far as I remember, is 8 planets around the star. Just what was it? 2.5 years ago, there was this famous 7 Earths system, where star was found to have 7 planets, all more or less within a factor of 2 the size of Earth at different distances. 2 or 3 actually in the habitable zone. If, big if, they have what it would be liquid. Okay? 7 discovered all at once. And sometimes 4, 3, 8. Now, what happens? You get the shifting now is not as simple, right? So if I have only one planet, so suppose the kids are gone, if we had one kid, I really refer to the planets as the kids, okay? I say it's like parents with the kids, okay? And by the way, we have many situations where the planets have 2 parents, 3 parents sometimes. I joke with the students, I shouldn't be saying this, but I say it. Even the stars sometimes are polygamous. 4. A situation where 2 stars like this orbiting each other. More than half the stars in the sky are binary. I call them married. Okay, so they go like this, and sometimes you have another 2 like this, and these 2 are going around these 2 like this. And then sometimes you have a planet. It's an incredible system. Incredible system. Sometimes you have these 2 going around each other like this. You have one star sort of watching them, going around them like this, like keeping an eye on them. And then sometimes you have a planet or 2 going around like this. Incredible systems we have found. Anyway, so if there's only one planet, if I'm a star, I like to think of myself as a star. Everybody does. So if there's a planet going around, then as I said, I would be doing this. Huh? So my orbit would be very simple. And when I'm moving towards you, you see my spectrum shifting toward the blue. Then here, normal. Then here I'm going back, so my spectrum is shifting toward the red. Now here it's normal, or it's normal spectrum. Here now, moving toward you, shifting toward the blue. So it will be just doing this normal. Now, if you have 2, 3 planets, and each one is at a different distance and a different mass, so it's shifting me. So you can imagine my motion. I don't want to do that. People would think I'm dancing. Okay? Okay. You understand? So you get the spectrum. All you have is the spectrum. And you see the spectrum going. And people have very sophisticated computer codes that analyze that to Fourier transform or whatever, and figure out, or at least come up with a model. You say, I think the way to explain this spectrum and what it's doing is if you have 2 or 3 planets or something doing this and doing that and shifting and moving. And that's how we figure it out. There has been 1 or 2 claims. I think the community of exoplanets, of which I'm not, I don't do exoplanet research, has not accepted this, but there have been claims of a planet having a moon, also detected, so-called exomoons. So suppose up to the level that people accept and say, yeah, okay, this is very strong as an analysis. Sometimes, like, the uncertainties are too high, say. Uncertainties are too high, say. You cannot conclude that. Yeah.
Thank you very much for a very nice and exciting talk. So I had a small question. I noticed that the size of the universe is an order of magnitude of greater than the age of the universe.
Oh, yeah.
So how do we reconcile these two, keeping in view that the speeds can be greater than the speed of light?
Yeah, but that's simply because the universe is expanding as the light comes to you. So suppose I send you a beam of light, and you measure the speed of light, and you measure that the beam of light has taken, let's say, 1/10 of a second, or 1 millisecond or something, to arrive. Then you infer the distance between me and you by multiplying this with the speed of light, right? But now, if I send you this beam and at the same time I am moving, then you have to take into account that the time that took the light to reach you, maximum of which is the edge of the universe, right? The distance that it gives you is going to be smaller than the distance at which I am now at. You understand? So because I am actually, since I sent you the light, I have actually moved. So what you measure is the time it took for the light to reach you, but not the distance I am at now, since I have been moving. And remember, the farthest place that sends you light, which takes the longest time, is the one that is moving the fastest. So it will have increased the distance between it and you by a factor of something like 4 or something, 3 or 4. Yeah.
I'm not even sure if I should ask this question right now, but while listening to the talk, I had this question popping in my mind that how is this expansion of universe going to affect our galaxy? If you have any
Very good question, actually. Very good question. The reason why this is a very good question is because this Hubble constant that I have been talking about, H0, it's been a long time since I used white chalk like this one. If you remember the numbers, and most of you would not have understood the numbers because you're not astronomers, the numbers are something like 70 kilometers per second per megaparsec. So what on earth is that? A parsec is 3.26 light years. Let's say 3 light years. Megaparsec means 3 million light years. Okay? So we're talking about kilometer per second per 3 million light years. You need to convert that to kilometers to get rid of this kilometer. So you would get a number, which I won't remember, very small, to be 1 over seconds. The point is, when you convert this to a number in 1 over second, you get a number that is extremely small. Extremely small. So the typical exercise I give to my students is I say, okay, how big is the solar system? That's a bit of a trick question, but since I will have taught my students, they should know, because depending on whether you imagine the solar system to be the sun and the planets, which is what the general public thinks, or whether you imagine it to be the sun and the planets and all the comets, including the Oort cloud, the size is much, much, much bigger. But to make it simple, the size of the solar system with everything in it under the gravitational attraction of the sun is about 1 light year. Okay? So I say, with the Hubble constant that you know, its value, what would be the expansion speed of an object at the edge of the solar system? And when they calculate it, they find something like centimeters per second. Which means you can forget about that. Because every other speed that this object has, orbital speed and whatnot, is orders of magnitude. Meaning, to make a long story short, this value being so small means it can only have an effect, an observable effect, over very large distances. Very large distances. So the expansion of the universe, which in principle affects all space in the universe, in practice, in effect, in reality, can only have a non-negligible value at very large distances, meaning extragalactic, in between galaxies. Yeah?
Professor, thank you so much for your talk. I have a two-part question. The first part deals with the Hubble constant. So I would like to know how do you predict the Hubble constant will change over time? So astronomers having the same lecture after 5 billion years, say, what value of the Hubble constant would they have in your predictions? And the second part is a rather vague question, but how do you even think that the creation or the formation of the Big Bang itself, is that a scientific question, and how should scientists tackle it?
Yeah. So the first question is almost impossible to answer scientifically now, and it can only be a scientific question, right? What will be the Hubble constant? What will be the expansion rate of the universe 5 billion years from now? The reason for this is we really don't have a good handle. We don't even know the nature and characteristics of this dark energy. So is this dark energy going to sort of dilute itself and its impact is going to disappear? So we are only in a phase of acceleration, but then it will slow down? Or will it continue to just push out and the universe will actually end up ripping itself apart? Because parts of the universe will be so far apart from each other, light cannot, which means they essentially become causally disconnected. We don't know what kind of dark energy we have now and what impact it will have on the expansion of the universe. Right now, it's accelerated. So I can tell you is within, let's say, 100 million years, the Hubble constant will be larger than it is now. Let's say it will be 75 or something, right? But if you say, okay, in 1 billion years, probably not less, probably 75, 80 at least. Within 5, we don't know because that's a longer term and I don't know how things will have evolved. It's very hard. There's all kinds of models depending on the nature and characteristics of this dark energy and the dark matter, which we haven't yet figured. By the way, in 20 years ago, if I had given this talk 20 years ago, and I would have shown you, remember that pie chart that said, okay, here's how much there is ordinary matter, 4.9%, and then dark matter, 26.8%, and then dark energy, 68%. 20 years ago, we didn't have dark energy. We didn't know about it, right? So if I had shown you a pie chart, I would have said, we have about 10% according to astronomers, of normal matter, and they say something like 90% dark matter. Now that 90% of dark matter has now dropped to 26. Something else has popped up. It's, as I said, we're making a lot of progress, but at the same time, it's like new mysteries pop up. So that is very difficult to answer. The second question is also very difficult from another angle, because can we, if you ask scientists in general, they will say, of course, the beginning of the universe, including the t equals 0, the creation, emergence, appearance, call it what we want, of the universe. They say, of course, it's a scientific question. But then we say, but in science, nothing can occur from nothing. You can't have something from nothing. And they say, yeah, but if you have some vacuum energy, you say, vacuum energy from where? From what? You have to have some. You say, oh, quantum. You say, so you have quantum mechanics already, right? So that's not nothing. So you start with quantum mechanics. Even if you start with no matter, you already have quantum mechanics. So you have a universe with some laws, even if it contains nothing. You say, yeah, I have quantum mechanics and I have a vacuum. I say, that's not nothing, right? So it is a very difficult problem or question to address. What does science do when everything in science says you can't have something out of nothing, and yet the universe seems to have appeared from nothing? Do you give up when you just say, okay, this is a theological question, and okay, just that moment, we can't answer it scientifically, we have to answer it religiously or whatever, and then from that moment on, okay, scientists, you can do that. Is that acceptable? Maybe, maybe not. I don't know. We'll see how things evolve.
So, I'm a biologist, so excuse my naivety about physics. So, when we talk about Big Bang and those two little dots which expanded or the Big Bang happened, so I was wondering, so let's say those two Big Bangs and those two little dots which are where everything was.
One dot. Why two dots?
Okay, one
dot.
Okay, so that exploded.
Yeah.
So that was, let's say, that was in this space, which is a room, and then that is expanding, or the whole universe was in that little dot.
The whole universe was a dot. Not only the whole universe was a dot, the whole matter and energy and space and time was a dot.
Okay. And now the space is unlimited, infinite.
That's another problem. So, in principle, if we just limit ourselves to this Big Bang, that point has expanded and has given this huge universe, which we talked about a moment ago. We said this 90 billion light years across, right? Now, that is the observable universe. There is another part of it which is hidden from us, which would have sort of expanded like this, so I can see it because it's beyond my horizon. So the entire universe with the observable, non-observable universe is one big bubble, if you like, of space-time. Yes? Now, there are two views on this. That's the universe, that's it. Whether there are other universes or not is a different story. And some others say, no, that's just a local bubble in an infinite universe. There is no evidence for this, so this is just sort of a conception. This is the way people imagine it. So they say, no. There is an infinite universe, and there are universes that appear. So our universe appeared here and grew like this, but grew within an infinite universe. So what we do with the science I showed you is not that infinite universe, which I have no way of reaching. This is just someone's conception. I personally don't subscribe to that, but that's not a scientific question. What we do with this cosmology is this point which either appeared in nothingness or appeared in this infinite universe, and then exploded out like this, like a big bubble, and that's our universe. Yeah.
All right. So probably two last questions.
Hello. So I have a quick question. Are you familiar with new research that that says that there are markers of life on one of Saturn's moons, Enceladus.
There are what?
Markers of life, like those
Markers of life.
the
Yeah,
markers of life that we also-
biosignatures.
Biosignatures, yes.
Yes.
So my question is that
Biosignatures, what did you say?
Enceladus.
Enceladus.
Yeah.
No, I don't think there are any biosignatures.
So there are macromolecules.
So there are macromolecules. That's different.
Yes. But does the theory about the habitable zone still apply? Because when I asked the scientists who discovered these macromolecules on Enceladus, they said that we're moving away from that theory, that the habitable zone is not applicable anymore.
Yeah.
Life can be found outside the habitable
Yeah.
zone. So if that's true, then why are we looking for exoplanets only in the habitable zone?
Yeah, very good. Okay. No, we're not looking only in the habitable zone. I'm saying the planets that would be in the habitable zone, which I'll explain in a minute, would be a lot more exciting to us. But of course, we're looking for exoplanets anywhere they can be, and who knows, we might be surprised. Something that we think is outside of the habitable zone, and then lo and behold, it has oxygen. Who knows, yeah? But now, what do we mean by habitable zone? This word is a bit confusing, because people think habitable means where you will have life. Well, habitable means what? I know, you know, and I know what the actual definition is, but I say people in general, in the general public, they think this is where we could live. Whenever there is such a discovery or something, and I post on Twitter, they say, "Oh, so you mean we could live there?" I say, no, I don't mean where we could. Habitable in Arabic actually is translated, I don't know, in Urdu, قابل للعيش, where we may live, or where one may live, literally speaking. Okay, habitable, people think this is where we could live, or where life could exist. In reality, habitable simply means where water would be liquid. Period. Okay. Now, why would liquid water be such an exciting thing? Because, and here I speak under the guidance of these biologists, if I say anything stupid, just stop me. Macromolecules, not just macromolecules, complex molecules that would lead to DNA and RNA and all of that, are infinitely easier to form in liquid water than you could form them outside the molecules on Titan, where we know Titan, another moon of Saturn, doesn't have any liquid water for certain, but it has liquid ethane and methane. Like, yeah, so well, it's liquid and it is organic, so God knows, maybe. So where life could exist, potentially anywhere. We know that there are these extremophiles, they are known as, these organisms that exist in some places where you think, how on earth could they survive? But life is hard. It survives in extreme conditions. But that's extremely improbable. It's not impossible, but extremely improbable. So if I give you two cases and I say, okay, you only have limited resources to search for life. Look for this place here, which is a planet with an atmosphere and is in a place where if it has water, and by the way, water is a very easy molecule to make in the cosmos. So if you have an atmosphere and if you have a rocky planet with a good pressure, etc., very likely you will have water, and if there is water, it will be liquid. You want to look there, or you want to go look at Enceladus. Look for life on Enceladus if you want. I'm sure everybody will say, "Oh, let me look there first. My chances of finding life there are much better." Does it mean it cannot be found over there? No, it doesn't.
So I know when the canvas in front of us is the entire universe, the questions are never ending. But we can have one more question, but I would like to see some of the kids have any questions you would like to ask a question. सवाल पूछना है कोई आपने? पूछना है कुछ? हाँ, बिल्कुल. उर्दू में पूछ लो. उर्दू में इंग्लिश.
I want to know what the big wave means.
Wants to know what? Where the ozone layer is. Okay. Yeah, very good, very good. So ozone, first of all, ozone is a molecule, it's 3 oxygens together, okay? Instead of having normal oxygen, which is what we breathe, and we use to do chemical reactions in our body, which is O and O, yeah? O2. Suppose you have 3 molecules of oxygen like this, and they make a triangle like this, that's O3, yes? Now there's a layer of the atmosphere of Earth at about 50 kilometers above the Earth, and it is a somewhat thin layer where there is quite a bit of ozone. So we call it the ozone layer. Now that ozone layer is extremely important because it absorbs ultraviolet radiation from the sun, UV. O3O, by being 3 molecules like this, it has certain chemical properties where it absorbs the ultraviolet. And so as it is in that layer of the atmosphere at about 50 kilometers around us, it is extremely important. If we destroy it by sending some pollution that breaks oxygen 3, then the ultraviolet starts to come down and starts to make some cancer in our cells or destroy some life and all kinds of nasty things. You understand now? You understand? Very good. Thank you.
All right, so with this, I know that our questions will never end on such a fascinating topic, but we would like to give a big round of applause to Professor Guessoum. And we wish and hope and also pray that we can see you again in Pakistan very soon. Thanks a lot. And thanks a lot to all the people who came from outside LUMS. And thank you very much.